Okay, let's get started. So we've covered some ideas in memory scheduling so far. There are actually more ideas that I didn't cover here. But one thing that's apparent to us based on all of this is there needs to be more done in this area. Plus, the interface between the operating system and the memory scheduler is completely non-existent today as far as we know. Basically, operating system is doing some scheduling, memory scheduler is doing some scheduling, and they have no understanding of each other, basically. And they have no influence on each other also. So one thing we've discussed so far is this waiting for memory, for example, right? Some threads are waiting for memory for a long time. The operating system today is not aware of that, right? The operating system schedules the threads. It thinks they're all computing, but some of the threads may be actually waiting for memory and getting delayed. That information is not really accounted for in the OS, as far as I know today. And the memory scheduler also has no idea which threads operating system is prioritizing for whatever reason. So I think this interface is broken, and some of these papers try to patch that interface a little bit, but there needs to be a much better look at that interface today. Okay, so now that I've developed some basic ideas, now let's deconstruct this ranking. Because as you can see, we're increasing the complexity, except for the Atlas scheduler. All of the schedulers that we've discussed are actually reasonably complex schedulers. So at some point, it's good to take a step back and say, okay, do we really want all of this complexity in the system? And that was what we looked at in one of the past few years. Can we actually get rid of some of this complexity while still getting a lot of the benefits? So basically, let's take a look at what we've done so far. Basically, we've developed a lot of application-aware memory scheduling mechanisms, or you can call it the thread-aware memory scheduling mechanisms. And memory scheduling has become thread-aware. It's aware of the threads. It monitors the behavior of the threads. It forms a ranking of the threads. And I motivated the principle of ranking, which is a good principle. And the memory controller basically assigns a rank to each application and tags the different requests of different applications with the rank. And it basically uses that rank as part of the scheduling priority. And different schedulers use that in a different way, right? That's good in terms of performance, but the problem is full ranking actually increases a lot of complexity in the scheduler. Complexity meaning critical path latency and area. The goal is to improve performance and fairness, but is it worth to actually do all of that to have a much more complex scheduler? Sometimes you could actually design around it such that your critical path doesn't increase. Usually you can actually do that. You can overlap a lot of the latencies, but that increases your complexity of design in the memory scheduler. So that's what we wanted to do, basically. We wanted to look at not only performance and fairness, but also simplicity. So we're going to add another dimension to this. Ideally, you would like to be best at all of them, right? But it's not easy to do that. So if you look at simplicity, simplicity is evaluated in this paper as area as well as frequency, and you can read the paper for more detail. We actually have RTL implementations of different controllers, and we compute the area, we compute the maximum frequency. And we don't extremely optimize all of the schedulers, so some of the schedulers actually don't meet the frequency requirements, as I might show, although the paper has more detail. So, okay, that's the ideal. First ready, first come, first serve gets you here. It's application unaware. It's very simple, but it falls short on fairness and performance. And these other schedulers that we've discussed are all somewhere over here. As you can see, PowerBS is not very simple, but it's much more fair and it's high performance. Atlas is actually closer to FRFCFS in terms of simplicity, but it's not fair and it's higher performance. And TCM is somewhere here, as you can see. So in this implementation, actually, PowerBS was more complex, but I'm not sure if I completely believe that. Anyway, PowerBS and TCM are quite complex over here. So they're application-aware schedulers. They do ranking. And we don't want that complexity. So now we're going to try to design something that will hopefully not give up simplicity to optimize for performance and fairness. And the solution that I'm going to describe is something that gets here. Well, of course, this depends on the workloads and tuning again. But it's actually very close to the simplicity of FRFCFS. And the observations are twofold, basically. We don't want to do ranking, but we want to do grouping. And what does that mean? As opposed to monitoring and ranking, we want to somehow form two groups, or two ranks, if you will, as opposed to full ranking. And we want to classify applications very quickly into vulnerable and interference causing. So how do you do that? That's the key question. And vulnerable applications are quickly going to be prioritized over this one, and we'd like to have the ability to switch between two groups relatively easily. If you do full ranking, it's not easy to switch between two groups because the rank is, let's say if you have 24 threads, that's basically, if you have ordering, that's a lot of threads that you order, right? How do you shuffle that ranking? It takes a long time to actually switch. Whereas if you do this sort of grouping, maybe it's easier to switch between the groups. So this is clearly lower complexity compared to ranking. It's 1 bit as opposed to whatever bits that you need to encode the ranking, right?
Is this within a rank? Within a batch?
So in this case, I'm not even going to talk about a batch. Well, I'll give you a mechanism that doesn't even have batching at this point. You could add batching on top of that, but we haven't explored that really. Okay. So the second benefit is hopefully lower slowdowns than ranking, because one of the downsides of ranking that we realized over time is if you don't change the ranking easily, things that are ranked somewhere over here at the bottom get deprioritized for a while. That leads to slowdowns, fairness issues. That also leads to performance issues. So it's hard to analyze also some of the implications of the ranking. Okay. So then the key question is, how do you classify applications into these two groups, vulnerable and interference causing? So this is actually something we discussed earlier, very little. And the idea is this. If you actually serve a large number of consecutive requests from an application, that is the thing that causes interference. Basically, it's streaming threads cause interference, right? So what we want to do is we want to group applications with a large number of consecutive requests that are recently serviced as interference causing, and we want to blacklist them for a short period of time. Once they're blacklisted, they're deprioritized. And we'd like to clear the blacklist very quickly so that they actually get a chance to be blacklisted again or whitelisted again. Right? That's the idea. This is very dynamic. You quickly adapt. As you can see, it's thousands of cycles. The blacklist doesn't last for a long time. Whereas in the previous cases, ranking lasted for millions of cycles sometimes. So it doesn't adapt very well. This is a mind of its own. It's moving by itself. Let me fix this if I can. Okay. What do you think? It's a basic idea. It's the idea of the blacklisting scheduler. The benefits is it's lower complexity because that blacklist you can easily form. And you get very fine-grained grouping decisions. And this actually leads to a much more agile scheduler. Although the previous schedulers, including Atlas actually, are not agile. They don't change their rankings very quickly. Here you're very agile. You quickly blacklist and you quickly not blacklist something. Of course, it's still threshold-based, so it's still not extremely satisfying, this part especially. And it's also, there's a threshold for blacklisting also. When does an application get blacklisted? How many requests should it get serviced? But at least if you make wrong decisions, they don't last for a long time. You quickly whitelist. Okay, and this actually buys you somewhere over here. Okay. So basically, it's close to ideal, but take this with a grain of salt, that with optimized parameters. So let's look at the performance and fairness of this. And you can read the paper for more parameters. So I believe things get blacklisted after maybe 6 requests, and they get blacklisted for 2,000 or so cycles. But those are all varied in the paper. And these are the results that we see, basically. Okay. So blacklisting performance is somewhere over here. It's better, but it's not the most fair scheduler, as you can see. There are more fair schedulers. PowerBS is quite fair, for example. And then these applications, the 5CFS cap tends to be fair also. Okay, complexity is interesting. This is a scheduler area according to our implementation. Ideally, you would like to be here. And this is the critical path latency according to our implementation again. And these are not extremely optimized implementations, I must say. Some things are on top of each other. So PowerBS is very far away, as you can see over here. Atlas is here. TCM is here, and blacklisting is close to the simplest schedulers, FRFCFS and FRFCFS cap. Yes?
So when you're blacklisting, you're basically reducing the resources of your memory controller because some of the requests you're not serving.
Again, this is a priority order. So for example, let's assume that you blacklist, if you've serviced 10 requests consecutively from an application, you say, oh, this is blacklisted. You basically reduce its priority to interference causing. If there are any requests coming from a non-blacklisted application, that gets prioritized. But if there are no requests coming from a non-blacklisted application, you can still use the memory bandwidth for this application. So we don't waste bandwidth.
The criteria is number of accesses within a window, within a
Exactly, yeah.
epoch. So
Actually, that was our criteria, number of consecutive accesses that are served for each thread. So if that consecutive thing is broken, so basically you're the memory controller, you're serving requests. If the next 5 requests that you serve are from this thread, then that's blacklisted. Yeah. No interfere, exactly. If there's something that interferes, then you reset the counter.
Okay.
Basically, you can implement with a single counter.
Yeah, okay.
Of course, is this the best policy? I mean, you could do blacklisting in many different ways, but this is what we looked at. So it's very simple in terms of the implementation. Okay, if you want to learn more about it, you can look at the paper. Actually, this is a longer version of the paper that has a lot more detail. Any questions? So now I've deconstructed a lot of things that I've built up to. Yes?
So this doesn't address at all trying to organize the request in a way that will cause a lot of hits. The contrary. And even though it does improve the throughput.
Yeah, so it doesn't directly address because you're still using the basic algorithm for a row hit first, right? You just have another priority level on top of that, which is blacklisted or not blacklisted. So it does improve throughput because of that. If you're not blacklisted, if no one is blacklisted, this goes back to row hit first, existing scheduling mechanisms. And if everyone is blacklisted, you go back to that over there, but everyone doesn't get blacklisted, basically. Well, they could, actually, if your blacklisting interval is long, and there's a possibility that that happens, but of course, it doesn't happen often. So I think the current realization is that I think these agile algorithms are usually better from my perspective. You can quickly adapt. But there may be better algorithms, of course, right? I think some of the principles that we've discussed are useful, but we haven't done enough work beyond the blacklisting scheduler to figure out how they could be combined with each other. So I've given you a lot of principles, actually. Batching is still a very good principle, in my opinion, but it's not, we don't employ it over here at this point.
Having like 4 beans instead of 2 changes anything? Or
For,
you don't want to
oh.
do a full ranking of.
Mm-hmm.
So having
Yeah.
few beans
Maybe, yeah, but we haven't looked at it. I think.
you know, like bunch predictors. Bunch predictors. So basically, you move.
Yeah, you move between multiple. Yeah, I'm not sure. I think if,
I don't know.
yeah, if you can somehow, maybe you have different categories of blacklisting, basically, what you say, right? Yeah, I don't know. That's why I think there's room for exploration over here. Okay, let's switch gears a little bit. Let's look at something else that we did before the blacklisting scheduler, but I think this addresses some other problem. We were very concerned with scheduler complexity, plus also other issues like heterogeneity. So far, I'm assuming that you have cores, right? They're generating requests. But life is not that simple also, right? You have cores and a GPU and a hardware accelerator. So you want to take that into account. And if you take that into account, you want to make your scheduler still simpler on top of that. So how do you do that? So I'm going to give you some ideas over here. Basically, if you actually are doing memory scheduling when you have a GPU and a CPU, you need a scheduler with large request buffers. And if you have an application over a memory scheduler like we've discussed so far, they're hard to scale to large request buffer size because these are actually heavyweight algorithms that, like we've seen before. So we wanted to do something different in this case. And this is a very different idea. We call it the stage memory scheduling. And there are several ideas in here. One idea is to decompose the memory control into 3 simple stages. One is basically you divide the functionality into 3. One is you form batches to maintain row buffer locality. Basically, form batches of requests that go to the same row. And you do that very early on, maybe even close to the course. When you're actually generating the requests, you basically form as a batch. And then you have a scheduler of the batches that basically looks at these different queues and tries to reduce interference between the different cores, CPU, GPU, different CPU and GPU cores. And then the last portion of the scheduler is essentially very simple. It's FIFO. It's the DRAM command scheduler. It just issues requests to DRAM. And this is actually also a simpler scheduler and more scalable, as we've seen, and to provide high performance and fairness. We'll see that. But basically, this is the problem that we're looking at. You have a bunch of cores and a GPU, and the purple requests are from the GPU, basically. GPU dominates everything, essentially. But these are also important because you could have latency-sensitive things over here. So we want to, if you actually employ a heavyweight algorithm like PAR-BS or TCM on top of this, it doesn't scale very well. Its complexity is a lot because the request buffers are huge. So we're going to divide the scheduler into 3 stages, and we're going to push the queues closer to the cores. The first stage is batch formation. As you can see, you form batches that go to the same row. And then the second stage is scheduling of those batches. So how do you actually choose between these different queues? And the last stage is dividing the requests to go to go to the banks. So batch formation looks like this very quickly. You basically group requests that go to the same row. So GPU, for example, has very good row buffer locality. It has very large batches. And you can encode the batches in simpler ways also. You could think of this also as increasing the granularity of scheduling. You don't schedule at the granularity of a single request, but you schedule, at least at this level, at the granularity of a batch of requests that go to the same row. Maybe you can encode that, oh, this request goes to row X, and you need this bit vector from that row X. Bit vector meaning these are the cache blocks that I want from that row X, right? And the next step is how do you actually decide between these two? I'm going to talk about that very briefly. And the next step is the command scheduler. So how does this batch scheduler work? Again, this is still a work in progress, I think. But basically, there are 2 fundamental choices that you can make as an example. You can actually round robin between these queues for fairness. Or you could pick the shortest job first, which correlates with whatever we talked about earlier. Shortest job first maybe says that, oh, this core has fewer requests over here. So if you pick shortest job first, you schedule the request of this core. And then you may switch to round robin. And then you do the round robin. And then, yeah, basically the scheduler works by picking between 2 policies, depending on some criteria. And if you want to really know the criteria, you can take a look at the paper. But you can probabilistically switch between them also. One of the things that we will use is the importance of the GPU and its weight that I'm going to show you. OK, that's the basic idea. So there are two ideas here. One is you decompose the scheduler into 3 stages as opposed to having a single monolithic scheduler. That simplifies the scheduler. And the second is stages are specialized as to what they do. And this batch scheduler is where the real complexity is in the end. That's how you select. And you could actually employ many different things. That's why I'm not talking about that in detail over here. So complexity, according to even a row hit first scheduler, across a very large queue, it turns out this consumes less area and less static power, and less dynamic power also, but it's not on the slide. The reduction really comes from this monolithic scheduler. You have, as opposed to a huge monolithic scheduler, you have stages of simpler schedulers. And each stage also has a simpler scheduler because it considers fewer properties at a time to make the scheduling decision. And each stage has simpler buffers, basically. The first stage has FIFO buffers, and the last stage also has FIFO buffers. First stage is not exactly FIFO because you need to accumulate access to different rows. You just need to keep track of which rows over there. And each stage has a total portion of the total buffer size. Buffering is actually distributed across the stages right now, as opposed to being monolithic. OK, so we've done some performance experiments. So this is not easy performance experiments to do because you have a GPU and you have a CPU, right? Or CPUs. One thing that we try to do is look at how important is the GPU at any given point in time. So if you might have a GPU weight that's really high, meaning that you should prioritize the GPU over here. Or you might have a GPU weight that's really low, meaning that you should prioritize the CPUs over here. And if you look at the best previous scheduler, it looks like this. Atlas turns out to be good for this regime. TCM turns out to be good for this regime. And FRF-CFS turns out to be good for this regime. Row hit first scheduler that naturally prioritizes the GPU. Atlas naturally prioritizes the CPUs, which makes sense, I think, if you think about it. And if you're somewhere in between, now you're more heterogeneous, right? If it's not clear which one's more important, you may want to have a heterogeneous path. So the principle, this picture is, I think, very telling, because if you know the principles of how these algorithms work, this makes a lot of sense. Which one's performing the best previously makes a lot of sense. Because GPU has a lot of robot for locality and very high intensity, whereas CPUs have very little intensity. They may or may not have robot for locality. Okay, so if you use SMS, stage memory scheduling, this is the performance that we get. Basically, what we do over here is, based on the weight of the GPU, we probabilistically switch between shortest job first and round-robin policies. If the GPU weight is, maybe there was a FRCF result. I don't remember, so don't quote me on this, but take a look at the paper for more detail. But based on the GPU weight, you switch between different batch scheduling policies. That's the idea over here. And if your GPU weight is really high, you're very similar to FRCFS, as you can see over here. If your GPU weight is very low, you're better than the best previous scheduler, which is Atlas over here. Okay. And if you're more interested, you could take a look at that. Any questions? So this is just one example of scheduling becoming more complex as you increase the heterogeneity in the system. Now you need to cater to different demands of the workloads. I'm going to make this even more complicated. This is the last scheduler that we've done so far, and let's take a look at what it is. The problem is it's going to be complex, but it's going to also cater to demands of hardware accelerators as well, because you really need to deal with all types of agents that are coming into you. In a system like this, you have a scheduler that's doing that, right? Okay, so basically, this is the system that we're dealing with. You have CPUs, hardware accelerators, and GPUs. I'm going to assume GPU is just another hardware accelerator for now. You have heterogeneous agents, and main memory is shared between them, so you have interference. So the key question is, how do you schedule memory requests between these CPUs and hardware accelerators to mitigate interference? I'll give you a very quick summary. You may not be able to understand everything over here, but that's okay. You can read the paper if you're interested. Basically, yeah, I already said that. We'd like to design a memory scheduler that improves CPU performance while meeting hardware accelerators' deadlines. The big difference between hardware accelerator and CPU is hardware accelerators have deadlines. And if you know the deadlines, you can schedule them. The challenge is different hardware accelerators have different memory access characteristics and different deadlines. A video encoder is very different from something else, right? And current schedulers do not necessarily smoothly handle them. Basically, you may have some memory-intensive hardware accelerators and long deadlines. Basically, deadlines are over a long period. And they degrade CPU performance because at some point you say, oh, I'm going to miss the deadline for this particular hardware accelerator, so let me make that hardware accelerator high priority in the memory controller. Now, the problem is when you raise that priority, this degrades the CPU performance significantly. Right? And there are also short deadline accelerators, meaning the deadlines are relatively short. You need to meet a shorter delay requirement over there. And they sometimes miss their deadlines despite giving high priority. So how do you handle them? And the paper actually discusses different accelerators. You can take a look at it. So the ideas here are basically you need to cater to different demands of different accelerators. There's no other way that we could find out. It's not, life is not that nice because everybody has a different requirement over here. One idea is, for example, you prioritize the hardware accelerators over CPUs anytime when the hardware accelerator is not making good progress. You monitor the progress the hardware accelerator is making. If you think it's falling behind, you prioritize it at finer grain intervals, as opposed to wait until the deadline and schedule all of the requests of the hardware accelerator right before the deadline. That gives little flexibility, but you keep track of the progress that you made. And we introduce application awareness also. Yes?
How do you define a good progress?
Yeah, that's in the paper. Basically, you know the demand of an accelerator. Usually it's specified as requests per a given interval. And you take a look at how many requests you're satisfying per a given interval. And if it's less than some expected progress given the amount of time you spent, you say you're not satisfying the demand. Does that make sense? Yeah.
So the memory controller supports
Memory controller supports that, yes.
to know which accelerator, what's okay.
You need to. Otherwise, as far as I know, there's no way. Basically, somebody communicates these demands to the memory controller, and memory controller keeps track of progress. And as opposed to trying to fit, okay, I'm close to my deadline, so let me prioritize it. And if I prioritize, I'm going to meet the deadline. Yes, that may be true, but that's very intrusive. you basically do it over time. And over time, you keep track of this fine-grained progress. And if it's falling behind, you prioritize it little by little. That's the idea. And of course, we want to be application aware, so there's still ranking in the scheduler. There's application awareness for both CPUs and hardware accelerators. So you will see the scheduling policy in a little bit. So it turns out if you do it this way, you can actually meet the deadlines while improving performance of the CPUs for a wide variety of workloads. And yeah, basically it meets the deadlines. And the source code of this is also freely available, so you can play with it if you want to do it. I think I've already said a lot of this, but basically this is what we wanted to do. Yeah, I already said that also. So worst case prioritization is not always the best, as I said. You don't want to prioritize at the worst case. So prioritize when and the hardware accelerator is not on track to meet a deadline. So you basically distribute the priority over time. This mitigates the impact of accelerators on the CPU core's request, as opposed to doing it right before deadline. You may still meet the deadline if you do it right before deadline, unless it's a really short deadline accelerator, if you do it before deadline. But then that is very disruptive to everything else in the system. Okay. Okay, I think I already said this also very quickly. So if you have a short deadline accelerator, we basically schedule them based on worst case memory access time. So if your deadline is going to happen very soon and very regularly, we basically assume that they're going to see the worst case memory access time, and they're going to be scheduled and somehow prioritized because they're important. Okay. Basically, not all CPU cores are also equal, and we know that by now. Some memory-intensive cores are much less vulnerable. Memory-non-intensive cores are much more vulnerable. As a result, we prioritize accelerators over memory-intensive cores to ensure accelerators do not become urgent. So that's, again, a design choice that we made because of the other insights that we've discussed, right? Accelerators are prioritized over memory-intensive cores. And these are the key ideas, basically. I think I've already said that also. So this is the scheduling policy. It's not nice, but this is how it is, because you have these different accelerators. So short deadline period hardware accelerators have the highest priority. Long deadline, actually, they sometimes have high priority. If they're, you schedule them based on the worst case memory access times, and based on that, sometimes they should get high priority. So when they have high priority, they have the highest priority. Long deadline period hardware accelerators, sometimes they have high priority if they're not meeting their deadlines. If they're not meeting their progress requirement. As a result, there's a second high priority. Memory non-intensive CPU applications are actually third priority. And long deadline period hardware accelerators that have low priority are over here, and memory-intensive CPUs are over here. And short deadline period hardware accelerators that are scheduled based on worst case and that are supposed to be low priority at that time based on that worst case are the lowest priority, because you've already scheduled their request based on their worst case. If you didn't understand that, read the paper. But basically, it's a complicated priority mechanism. And even here, it's not clear what's the best choice, so we switch probabilistically. I think probabilistic algorithms are going to be more important in memory scheduling. Here, this is really important because when they're high priority, you know that you got to service them. They should meet their deadlines. Over here, you have more slack and flexibility, of course. Right? And this doesn't even cover the case where CPU applications have deadlines. But if you think about CPU applications having deadlines, they should be treated similar to one of these categories. If you have a deadline requirement, you should specify it. Tell the memory controller about that, and CPU becomes like a hardware accelerator at that point in time, right? Okay.
How these deadlines are defined with something specified for the hardware acceleration or for the application that is in?
So application, yeah, basically whatever application you're executing. For example, GPU, right? You have a frame rate, let's say. Then you can specify that in terms of requests per some amount of time, right? That's the bandwidth specification. And you can convert a latency specification to a bandwidth specification also.
So why short is low priority is less prioritized than long is low priority? 4 and 6.
Yeah, so 6,
Explain that.
yeah, the reason is basically we schedule these, so we schedule these requests based on worst case estimates. Worst case meaning it's really worst case. You're really going to experience the worst case delays that are ever possible. Meaning that at some point, they have high priority when they need to send their request. So there are some intervals where they have high priority. As long as they're scheduled during that high priority, they should meet their deadlines because they're scheduled based on worst case. Right? And if they're not in a period where they're supposed to have low priority, you should schedule them. But if they have low priority, meaning that you schedule them based on worst case,
Priority is decided by the application or by
by the scheduling.
the schedule?
Yeah. So let's assume that you have a deadline requirement to meet.
Yeah.
And you assume that you have this many requests, and they're going to experience the worst case delay ever possible.
Okay.
If you assume that, you say, oh, the first request should be scheduled at time t. Until from time 0 to time t, you can't schedule that request, assuming you get that request. Let's assume you get it. But it's low priority for you, because your scheduling somehow charted out what should be done in the remaining amount of time based on all possible worst case delays. So between 0 and t, you're low priority. Now between t and 2t, let's say you're high priority. That's the idea. So between 0 and t, here you can, because you've scheduled these based on the worst case requirement, you're safe. That's why you can put them at the bottom. But if it's high priority, because you've scheduled them based on the worst case requirement, and the worst case requirement is important to you, they have to be at the top. That's the idea over here. Okay. Okay, I think this is really interesting, and we've actually experimented with real accelerators in this work, but there are many, many more accelerators to deal with. I think the main reason to read this paper would be to understand the complexity of SOC scheduling, because it's more complex than even what's described in this paper. Okay. So this may be a good place to stop. What do you think? And then we're going to switch gears, and we're going to talk about more predictable performance. Although we've kind of been switching to predictable performance, as you can see, with the hardware accelerator part.